Okay, I have a little demonstration here for you called a ballistic pendulum. This is the demonstration version of what they do to find the muzzle velocity of rifles and guns. Okay, our equation. Zero is equal to change in potential energy plus change in kinetic energy is only valid if it's only a spring or gravity causing your object to accelerate. Okay? It is not valid if friction is involved in changing the velocity of your objects. It is not valid if drag is involved in changing the velocity of your objects. It is not valid if there's any other push or pull changing the velocity of your objects. So this particular example. My gun is spring-loaded, so I have a spring over here. When I compress the spring, a little latch catches on. So right now, at this instant, our system is the ball, the pendulum, the spring-loaded gun. What type of energy exists in my system right now? Potential energy. The spring, elastic potential energy, has all of the energy. Okay, let's hope it works right. Let's try again. This thing's temperamental. Come on.
That was good enough.
Close. Here.
Trigger pull right there.
There. That's what's supposed to happen. There are rubber O-rings in that little pendulum that if the ball hits right on, just right, it gets stuck. And then the ball and the pendulum swing up. So right now, at this instant in time, what type of energy is there? Potential. But is it still elastic potential energy? No. It's gravitational potential energy now. Okay. Here's my question for you. Did all of that elastic potential energy turn into gravitational potential energy?
No. Yes. No. Do we have thermodynamics in here?
Friction.
Yeah, for friction on
So
the
rubber
pivot.
on that ball would cause friction.
And the pivot point on the fulcrum.
There's actually very little friction on the fulcrum because the screw, the end of the screw's hollowed out, and then the pivot is a point, like a pinpoint. So it barely touches. Drag, I can't imagine, is terribly significant in this case. But at any rate, there were forces acting on it that were not gravity and the spring. I guess that's really the moral of the story. We just said this equation only works if there's no friction, no drag, no other forces acting on it besides gravity and the spring. So this equation cannot work in this situation. The elastic potential energy we started with did not become gravitational potential energy to end with. So the elastic potential energy is 1/2 kx squared. The gravitational potential energy is the total mass of the ball and the pendulum together, G, Y. Those do not equal each other. The friction, the significant force in this case, is the friction between the rubber O-ring and the ball. That is a significant force that takes a lot of the energy out of the system. It's still total amount of energy is constant, but that is if we consider, for example, the thermal energy that was created from the friction. We take that into consideration, we can use energy. But I don't know how to find the thermal energy that was created without finding these first. Because we could certainly take the final potential energy and subtract it from this initial potential energy, and it would tell us how much energy was lost. Certainly, that would tell us how much was changed into another form. But I would need to know the potential energy and the final gravitational potential energy to do that. Okay. Let's break this into pieces. Before the ball hit the pendulum, what type of energy did it have? Kinetic. So we're talking after I pulled the trigger, but before it hit the pendulum. Where did the ball get that kinetic energy? From the spring. So we can say, before the ball actually hit the pendulum, that the spring's elastic potential energy became the ball's kinetic energy. That's perfectly valid. Friction did not act on the ball until it hit the pendulum. So this is perfectly valid. The energy was conserved before the ball hit the pendulum. Perfectly good.
Question.
Uh-huh.
Do we disregard the friction of the pin or the ball sliding out of the pin on the end of the...
Yeah, that friction, I mean, we could take it into account, but that friction is going to be awfully tiny, especially compared to the friction it will have with the rubber O-rings. Okay. What type of energy did the ball and pendulum have after they collided? They finally end up with gravitational potential energy, but I'm talking right after. Kinetic. So we can say after the ball has hit, so now the ball is stuck in the pendulum, we can say that the kinetic energy turns into gravitational potential energy. That's fine. This speed is not the same as this speed, though. This is the speed of just the ball before it hits the pendulum. This is the speed of the ball and pendulum stuck together, swinging up to get stuck at potential energy. So what do you think is going to form the bridge between these two? Say it louder.
I don't want that answer.
I heard something different.
That's why I just say it loud.
This is a collision, right? What is always conserved in a collision, regardless of what type of collision it is? Momentum. Energy is not conserved in all collisions. Energy is only conserved in elastic collisions, and this certainly was not elastic. Okay? But momentum. Momentum is conserved in every single collision, regardless of what type of collision it is. It can be elastic, it can be inelastic. It doesn't matter. That means the momentum that the ball had right before it hits the pendulum has to equal the momentum that the ball and pendulum have right after the ball hits. There's our bridge. This V initial was the initial speed of the ball that came from the elastic potential energy because the spring was compressed. The speed right after the collision is the same as the speed right here in terms of the kinetic energy that therefore turns into potential energy. So we can bridge the two. For example, it would be easy to measure the mass of the ball in the pendulum. Bring out a little scale. We can figure out how high it went, we just need a ruler. So we could easily find out this potential energy. Which means we could easily figure out how fast they were traveling right after the collision occurred. Which means we could easily figure out how fast that ball was traveling right before the collision occurred. That would be the muzzle speed. That's what they do to figure out muzzle speed of rifles and guns. It's a little more high-tech than this, of course, but it's basically a really easy way to find muzzle velocity. We could even take this one step further and figure out how strong our spring was. Figure out the K value for our spring. So it is possible that you may need to use momentum as well as energy for a problem. But you need to keep in mind when each of them are conserved. For example, momentum was not conserved if you look at the time of pulling the trigger to just before the ball hit. There was a force acting on it. That force caused the momentum to change. But energy was conserved. All of the stored energy in the spring turned into kinetic energy of the ball. Momentum was conserved during the collision, because momentum has to be conserved in all collisions. Period, end of story. Momentum was not conserved after the collision occurred, though, because there was a force of gravity causing the whole system to slow down. But energy was conserved. The only type of collision where energy and momentum will be conserved is elastic. That means your objects bounce off of each other. There's no permanent deformation. Ideally, no sound either. But the closest thing I can think of elastic would be bowling, the ball versus the pin.
Cool.
Assuming the pin doesn't ever break or the ball doesn't chip or anything like that. Billiards, playing pool, that would be close to elastic as well.